Welcome to my new calculus channel. My name is John Gabriel, and today I'm going to be speaking about constructions, the constructions that are found in Euclid's Elements. So let's begin. Now, a lot of ignorant mainstream mathematicians, they're not really mathematicians, I call them mathematicians, think that constructions are actually necessary in Greek geometry and mathematics. Actually, they're not necessary at all, but they do serve a purpose. And the purpose is namely this: to communicate these abstract ideas that we find, that we realize when we study geometry. So, the ancient Greeks had a clarity of thought that was matched by no one before or after them. They were unbelievably bright. I mean, there was no, you could not, if intelligence could truly be measured, and I don't believe IQ is a measure of intelligence, but a lot of people do, their intelligence was just off the charts. And you cannot compare it to any of the morons who have come after them in the last 2,000 years. A lot of people will say that Euclid's Elements is basic, but actually it isn't. Euclid's Elements is very advanced mathematics, and many have not understood it. In fact, the very translator into English, Sir Thomas Heath, did a great job, but he failed to understand the most important points, which is what exactly is a number. But I'm not going to go into that because I've dealt with that before. I'm talking about constructions here. So I need to remain focused, and I'm on a limited time. Heath didn't grasp the importance of the perfect derivation of number and what Euclid was attempting to do. But constructions are a means of communicating these abstract ideas. And why are they important? Well, because if you take a look at the elements, although it starts out simply, the proofs are incremental and they become very complicated. So, for example, here in proposition 1, do we need to construct an equilateral triangle to see that it's possible to have such a geometric object? Absolutely not, because if you have two circles with one whose circumference goes through the center of the other, and they're both of the same size, it's obvious that this length here is a radius of one circle, and this length here is a radius of both circles, and this length here is a radius of this circle here. Therefore, the sides must be equal, okay? So we only do the construction to show that it is possible to reify the abstract concept. And you may ask, well, why so? Well, if you get down to further propositions, like propositions, like this proposition here, 2, imagine communicating that without being able to construct the diagrams, okay? And moreover, imagine going to proposition 4, where we're no longer talking about the circle and we've got this little arc here on which the angle is subtended. And the proposition is based on this abstraction. So imagine not being able to construct this so that you can communicate the idea. Well, the proofs become quite complex as you move along in the book of in Euclid's books of elements. In his I'm getting tongue twisted, but if you move along, you will see that all the propositions are quite complex as you start off from the beginning. Now, I don't want to spend any more time on that. I'd like to show you now another great master of mathematics. In fact, the greatest mathematician, in my opinion, ever, Archimedes. And probably most of you will not have even tried to study these works of Archimedes, but I'm going to show you now how stupid mainstream academics are when they say that geometry was based on constructions. Imagine trying to construct a spiral. See this spiral of Archimedes using a compass and straight edge? You can't. Okay? So this here is a perfect idea, and Archimedes actually squared the circle using this abstract geometric object. And in fact, I have a video about that. It's called How Archimedes Squared the Circle, and you could go to it and watch it here on YouTube. And also, I have a link to the applet, which I use to demonstrate it. Okay, what it basically says, this proposition 18, is that this shaded triangular area is exactly equal to the area of the red circle. So you may ask, well, how did Archimedes square the circle? Very easily. If he could find a triangle with the same area, a triangle is half the area of a rectangle, isn't it? And a rectangle consists of squares. So Archimedes did square the circle, and he didn't do it with a compass and a straight edge, which is totally unimportant that it could be done with a compass and straight edge. And so constructions have a purpose. They're used in communication, mainly in communication. But in this particular case, notice that everything in here can be constructed excepting for the spiral itself. Okay, so the spiral cannot be constructed using a compass and straight edge. And this is very complex mathematics. Most PhDs will not understand what Archimedes wrote, especially his chapters on floating bodies, on the parabola, and many other incredible works that he wrote. And this PDF that you see in front of you is available for download. Now, I would not allow anybody, in my opinion, to be called a mathematician until they have passed an extensive exam on Euclid, Archimedes, and Apollonius. Okay, so Apollonius is even more intriguing than Archimedes' works and Euclid. So I would encourage you to download these PDFs and start with the very simplest one, which is Euclid's Elements, because the others are quite complicated. Now, when I was young and I had studied all these things, I didn't have advanced tools like GeoGebra or anything like that. So you can also use the CAS systems, any CAS systems you have to help you study these things, because when you can't really construct the ideas you're trying to understand easily, it takes much longer to study the same. So construction, although not necessary at all, by the way, because those geometric objects have always existed, whether the Greeks thought of them or not. And if there are other advanced alien civilizations, they could realize these concepts too, because they're not limited to the human brain or to any brain. They exist independently of any sentient being. In other words, the best way to categorize them is to think of them as noumena. So constructions are not necessary, but they are useful in communicating the ideas of geometry. So this is a very important video, and I'd like you to think about it. And in the next video, we'll continue discussing many more interesting things about mathematics, and we'll go back and forth if we have to. I don't believe that I shall ever finish this series, but I think that if you follow these videos that I'm going to post, you'll become much smarter than all the academics in the last 2,300 years. I also encourage you to download the most important mathematics book ever written, An Introduction to the Single Variable New Calculus. You can find a link to the free ebook if you just type in An Introduction to the Single Variable New Calculus by John Gabriel, and study the book, because you will learn more in that book or from that book than all the worthless textbooks ever written on mathematics or calculus. And so I hope you've enjoyed this short presentation, and that you'll join me again sometime in the near future. This is a new calculus channel, and my name is John Gabriel. Goodbye.